Intro. But energy. Powerful enough to cripple an entire coastal city. In just the last 50 years, storms and rising seas have inflicted up to $4 trillion in damage worldwide, forcing tens of millions of people to leave their homes. When water levels begin to rise, just a few hours can be enough to fracture critical coastal infrastructure. That is why humans have built breakwaters, the first line of defense between the ocean and the land. Not flashy, not mobile, but this is where the power of the waves is. Broken. Offshore. In today's video, join Quantivox Tech as we explore how these wave protection systems are designed, operated, and traded off to change the fate of an entire city. In the Netherlands, a country where nearly 1/3 of the territory lies below sea level, getting water control wrong can destroy ecosystems, inland navigation and coastal livelihoods. Oosterscheldekering was created as an unconventional solution, intervening only when truly necessary, while allowing the sea to operate naturally. For most of the time, it is the nation's most famous hydraulic engineering project, protecting the lower delta from rising seawater, and widely regarded as the eighth wonder of the world. At the peak of construction, around 1,900 engineers and workers were active each day. In the North Sea, the structure stretches nearly 9 kilometers, comprising more than 60 reinforced concrete piers, each weighing tens of thousands of tons, positioned precisely on the seabed, using specialized lifting equipment. Deviations of just a few centimeters could destabilize the entire structure. Between the piers are 62 suspended steel gates. Under normal conditions, the gates remain fully raised, allowing tides, marine life and vessels to pass freely. This open design preserves the saline ecosystem of the Oosterschelde, one of the most important marine habitats in the Netherlands. The system is activated only when forecasts indicate water levels may exceed 3 meters above the NAAP reference level. At that point, hydraulic cylinders gradually lower the steel gates over several hours, turning the inlet into a continuous barrier, capable of withstanding the force of North Sea storms. Today, the challenges extend beyond nature. Oosterscheldekering is undergoing upgrades to security and access control, including measures to prevent unauthorized entry onto the support piers, a problem linked to illegal fishing activity. Tetrapod. Not every coastal defense is built as a solid wall. In many cases, coastlines are protected by individual concrete blocks that appear chaotic at first glance. Yet it is precisely this intentional disorder that gives tetrapods their strength, making them one of the most effective coastal defense solutions ever developed. Each tetrapod begins with a high-precision steel mold, designed to ensure the four arms meet exact angles and proportions before concrete is poured. The mold is coated with a release oil, so it can be reused multiple times without damaging the surface of the cast block. The liquid concrete mix is then poured into the mold and subjected to mechanical vibration to eliminate air bubbles and internal voids. This step is critical because even a small weakness can cause the concrete to crack after years of repeated wave impacts. Once the concrete has cured, the 3-part mold is removed, revealing a completed tetrapod ready for transport. Each tetrapod can weigh up to 25 tons, enough to remain stable under repeated exposure to large waves. Tetrapods are typically installed offshore, using heavy lift cranes or specialized barges. The blocks are not stacked neatly like bricks. Instead, they are placed according to calculations that allow their arms to hook and lock into one another. This arrangement creates an interconnected structure in which forces acting on one block are dispersed across many surrounding blocks. If a single tetrapod is displaced or washed away, neighboring units lose support, weakening the entire defense line through a chain reaction. For this reason, precision during installation is critical to the structure's long-term performance. The cost of building 1 kilometer of tetrapod breakwater can exceed $10 million, depending on block size and sea conditions. However, this figure becomes small when compared with the damage caused by storms. In coastal defense, tetrapods represent a clear philosophy, not to overpower nature but to weaken its force in the most sustainable way possible. This block, when tetrapods had proven their effectiveness, coastal engineers began researching structures that could dissipate wave energy more efficiently while using less material. One such example is Xbloc. Xbloc is a wave attenuation block system developed by Delta Marine Consultants of the Netherlands with a key distinction: only a single layer is required to form a protective armor layer. Thanks to its self-locking shape, The X-shaped blocks interconnect as they are placed, creating a hydraulically stable structure. With high porosity, waves are not reflected back, but instead are dispersed and lose energy as they pass through the layer. Compared to Tetrapods, Xbloc uses less concrete, occupies less space, and reduces the need for precise alignment during construction. In terms of production, X-shaped blocks are still cast in concrete molds, but the process has been highly automated, shortening production time and ensuring consistent quality. In return, the system requires specialized factories and equipment. Today, Xbloc is being deployed along many coastlines worldwide, representing a clear trend. Coastal defense no longer relies on Massachusetts, but on geometry and the way wave energy is forced to dissipate itself. Great Wall of Japan. Great Wall of Japan. As an island nation, with an almost endlessly long coastline, Japan has been forced to invest on a massive scale in breakwater systems to protect its infrastructure from storms and tsunamis. Along the northeastern coast, from small fishing villages to industrial towns, a massive concrete wall runs parallel to the shoreline. In many sections, the wall reaches heights of 12 to 14 meters, equivalent to a 4 to 5-story building. When considered across the entire region, the total length exceeds 400 kilometers, enough to immediately evoke comparisons to a modern Great Wall. This is not a single continuous structure, but a sequence of defensive lines, some sections tall, others lower, some press close to residential areas, others set back against rocky cliffs. Each segment is individually designed to match local terrain and coastal risk levels. From an engineering perspective, this is a monumental water defense structure. Its foundations are deeply reinforced to resist erosion, while the concrete elements must withstand large waves, reverse currents, and earthquakes simultaneously. The total construction cost runs into tens of billions of dollars, making it one of the most expensive disaster prevention projects in the world. From the moment construction began, the system sparked intense debate. The towering walls block views of the sea, alter the landscape, and sever the traditional relationship between coastal communities and the ocean. In return, Japan accepted a clear trade-off, sacrificing the view in exchange for life. MOSE. This is the romantic Venice we are all familiar with, and this is a slightly less romantic version of it. Flooding is no longer a rare event, but has become a part of daily life here, with both its frequency and severity increasing significantly over the past decades. Beyond reinforcing shoreline structures, the city needed a stronger and longer-term solution. That is why the MOSE system was created, a network of massive floodgates designed to isolate Venice from sudden storm surges. The MOSE system is specially designed, with 78 floating steel gates installed at the 3 main lagoon inlets, with dimensions varying by location. Each gate is a massive hollow steel structure, approximately 20 meters wide and about 4 to 6 meters high. MOSE is activated only when tidal levels exceed 110 centimeters above mean sea level. Once activated, all gates rise, forming 4 continuous flood barriers. The gates are held at an angle of about 45 degrees, while the system continuously adjusts the amount of water inside each gate to maintain a safe and stable inclination. When the flooding event ends, water is pumped back into the gates to weigh them down, and they gradually return to their horizontal position. On the seabed, the system integrates modern mechanical, hydraulic, and sensor technologies, allowing water levels to be controlled with near-perfect precision. It also represents a major advance in lagoon research and management, providing valuable data on tides, currents, and climate change. Thames Barrier. Thames Barrier. Spanning the River Thames at Woolwich. The Thames Barrier is not a fixed dam, but a movable shield that can be raised and lowered against the tide, with a total length of approximately 520 meters. When it was completed in the 1980s, it was the largest movable flood barrier ever built, and to this day, remains an icon of urban hydraulic engineering. The entire system consists of 10 massive steel gates. The 4 outer gates function as fixed defensive sections, while the 6 large central gates are designed for flexible operation. Under normal conditions, the central gates remain open, allowing ships to pass and the Thames to flow naturally through London. The city almost forgets that this shield even exists when forecasts indicate that water levels may exceed safe limits due to storm surges, North Sea storms, or upstream flooding. The order to close the gates is issued. The process takes about 90 minutes, during which the steel gates rotate upward from the riverbed, forming a continuous wall across the river. Each gate can rise up to 20 meters, capable of withstanding the pressure of thousands of tons of water, pushing towards central London. During peak tide, the system remains closed for 4 to 5 hours, preventing floodwaters from inundating low-lying, inner-city areas. Once water levels recede, the gates are lowered back into position, restoring the river to normal navigation and daily use. In essence, the Thames barrier does not seek to tame the river Thames, it exists to intervene at precisely the right moment, for just long enough to protect approximately 1.42 million people and hundreds of billions of pounds worth of property. In London, it represents a modern form of defense, not permanent but always ready. A shield that appears only when the city truly needs it. Tetrapods and wave-reflecting walls. Along the coast of South Korea, which is frequently exposed to large waves from the Yellow Sea and the Sea of Japan, coastal defense does not rely on tetrapods as a standalone protective layer. Instead, engineers have developed a two-layer defense system, in which tetrapods serve only as the initial energy dissipation stage, while the decisive element lies closer to shore. The wave-reflecting wall is the first line of defense. Tetrapods are placed offshore as an active buffer zone. Incoming water is broken up, split and made turbulent as it passes through the interlocking concrete units. Behind the tetrapod layer stands a perforated wave-reflecting wall, a structure designed to handle the remaining energy of the waves, rather than presenting a flat surface for direct impact. The wall incorporates hollow chambers at its base, allowing water and sand to rush inside at the moment of contact. When water is forced into these cavities, pressure is not concentrated on the foundation, but redirected upward, disrupting the wave's momentum. Energy that would normally be focused in the horizontal direction is bent vertically, significantly reducing the force acting on the base. This is particularly important in limiting seabed scour, one of the main reasons traditional seawalls weaken over time. The combination of tetrapods and wave-reflecting walls is not intended to stop the ocean. Its purpose is to weaken waves step by step, divide risk and control how energy is released. This is how modern coastal engineering chooses to endure over the long term against an opponent that never stops moving. Before the vastness of the ocean, humanity has never truly been able to control nature. What engineering can do is only reduce risk, buy time to react, and create a fragile buffer between disaster and everyday life. Coastal defense systems, therefore, are not symbols of power but expressions of caution and an understanding of limits. Every wall, every concrete block, every steel gate is built on one clear assumption: natural disasters will return. The only question is whether we will be prepared enough when they do. As sea levels rise and weather grows increasingly extreme, the engineering decisions made today will shape the safety of coastal cities for decades to come. If these engineering stories offer you a new perspective on how humanity coexists with nature, please like the video, subscribe to Quantavox Tech, and turn on notifications to continue the journey with us in future episodes.